Good afternoon and welcome to Webinar Wednesday. Today we are joined by Lewis Leonard, Product Manager North America at Rigel Medical. Webinar Wednesday would like to thank our sponsor, Rigel Medical. Rigel Medical is renowned globally as a designer and manufacturer of reliable, portable and compact biomedical test equipment. As metrology specialists for almost 4 decades, their innovative testing solutions have been mitigating risk worldwide in healthcare environments. Their products ensure that critical medical equipment is safe to use throughout the device's life cycle. For more information, please visit rigelmedical.com. Now, just a quick reminder about our Spring MD Expo. We're headed to the M Resort Spa Casino in Las Vegas from April the 7th to the 9th. So please join us for 3 days of education, networking, and the latest advances in medical technology products and services. Registration is now open, so for more details, please visit mdexposhow.com. Also, please mark your calendars for our HTM Mixer, which is being held at the Westin Indianapolis, May the 2nd and 3rd. Now, our mixers are a slightly modified, smaller, shorter duration and less crowded event that still provides valuable continuing education, networking and vendor engagement opportunities. For more information and registration details about the HTM Mixer, please visit htmmixer.com. TechNation magazine is also excited to announce that we are taking applications for our 3rd annual 40 Under 40 powered by YP at MD. We are looking for HTM professionals who are under the age of 40 who have done amazing work for the biomedical industry. Applications are due by April the 26th. So please apply at one technation.com/2024-40-under-40 or see the flyer in the handout section of your dashboard. Now, today's webinar is eligible for 1 CE credit from the ACI, and you can attain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. Let's kick off today's webinar by giving away one of our Webinar Wednesday 10th anniversary prizes. Today's prize is another pair of Apple AirPods, 2nd generation. So using the questions feature on your dashboard, let me know the answer to the following trivia question. February is National Cherry Month. What state is the largest producer of cherries? I'll reveal the answer and our winner at the end of the webinar. As I mentioned earlier, our presenter today is Lewis Leonard, and he will be discussing navigating NFPA 99, selecting the ideal analyzer for your electrical safety workflow. This is a pre-recorded webinar, so there will not be a live Q&A session. If you have any questions for Lewis, please email him at the address shown at the end of the webinar.
Hello everyone, this is Lewis at Rigel Medical. Thank you everyone today for attending this webinar. It's going to be a 2-part webinar where I'll be doing a presentation on NFPA 99 2021, focusing on the latest test code, and also how to choose the right safety analyzer. So doing a demo with 2 very different safety testers. One is the manual Safe Test 99 and also the 288 electrical safety tester, which is a more automated comprehensive type of tester. We also have a application that's just been released for the Rigel 288 Plus, which is on both Android and Apple, and this produces test reports straight from the device to your phone. So I'm going to do a short demonstration as well with our latest application, which should help you streamline some of your workflows. I will be focusing on those 2 devices, but also elaborating on some of the other electrical safety testers that we have within our portfolio to see what's best fit for your electrical safety needs. The first part of this presentation is ACI accredited, so you can put that towards your continuing education units.
So firstly, a little bit about ourselves at Rigel Medical and who we are. We are renowned globally as a designer and manufacturer of reliable, portable and compact biomedical test equipment. we've got two operating locations, one here in Tampa, Florida, and the other in the UK, Peterlee, England, which is where our manufacturing facility is. We've also got 7 global authorized service centers around the world, and we have 40 plus distributor partners covering not just the US territories, but also around the world. So when any person or individual comes into contact with any type of electrical equipment, there's always that potential for electrical shock. The cardiac functions, the muscular systems, the nervous systems, they're all sensitive to the physiological effects of electrical current passing through the body. And this is especially true at all the worldwide frequencies. 50 hertz in the US has a significant physiological effect on the body when electrocution occurs. Now, with healthcare, there's a further risk from electrocution, and that is due to direct and constant patient contact with different types of medical electrical equipment. The human body is very conductive. It allows electrical currents to flow through. But fortunately, most of the human body's resistance is through the skin. And this is why it's considered such an effective barrier unless it's wet. Now, with medical equipment, you've also got the issue of applied parts. So human body comes into contact with any electrical current. We've got that effective skin barrier, but applied parts and any conductive emollients can allow the bypassing of that effective skin barrier. And this is in addition to being close to any cardiac muscles that are sensitive to really low currents. And moving on from that, this is where Ralph Nader's most shocking expose revealed that over 1,200 Americans were electrocuted annually during procedures. So this resulted from the increased use in cardiac catheterization procedures and external pacemakers during open heart surgery. And this means that minor electrical shocks can then lead to ventricular fibrillation. Now, several years later after the expose, the safety standard IEC 60601 was formed, and the revisions have led to year-on-year reductions in death from both macro and micro electrocution. And NFPA 99, which we're talking about today, is based upon that standard. So all of the electrical safety standards and performance standards originally derived from this expose to prevent the harm to patients within the biomedical engineering field. So it's led to a whole new sector for technical support and the users of medical devices in healthcare. So there's macro shock. This occurs when current passes through the body via contact with the skin, and this aspect applies to all types of electrical safety. Because of that high resistance, that dry skin has very high resistance, and that limits the current flow through the body. Macro shock, the effects are seen at much higher currents. So with micro shock, which we'll talk about in the next slide, medical procedures can often mean bypassing that skin barrier and being close to either the heart or just in conductive pathways. Now, with medical procedures, you've also got the issue of moistening the skin because you're using different emollients, surgical applicants. Ultrasound gel, for instance, is very conductive. And furthermore, patients are always in contact with medical electrical equipment. And that's both directly and indirectly. What I mean by that is medical electrical equipment, such as patient simulator, that's a device that's directly in contact, but you've also got indirectly connected medical devices, such as electrically powered beds. So there's all sorts of factors to consider with electrical safety within healthcare environments. So the results from macro shock, we've got leads to loss of involuntary muscle control, currents as low as 10 milliamps or 6 milliamps, and then ventricular fibrillation at currents at approximately 100 milliamps. And when we go on to the next slide and show you the effects of micro shock, we can see that the levels are much lower in the magnitude of 10 microamps, 20 microamps, you get an increased risk of micro shock. And this particular factor is unique to patients in medical environments. They are vulnerable to these risks, and they occur when invasive patient connections are placed in close proximity to the heart, and also to nerves. Any conductive points, such as blood components, also have very low resistance, and very low levels of electrical current can induce ventricular fibrillation, because anything below the skin surface is has low resistance, and current is also focused at invasive locations. Death by microshock is known as microelectrocution, and there's been several studies that have recognized the physiological effects of electrical current, and this is both for macroshock and microshock. These studies have been performed, and what you'll find is that international standards, NFPA 99, will always reflect those conditions and those effects, which is why you'll see that patient leakages have much lower test limit levels than those of equipment leakage test limits. And these shock risks, they come from things like intracardiac connections, pacemakers, or saline catheters, anything that's bypassing that skin barrier. Even ECG connections, they're placed very close to the heart. They might not necessarily bypass that skin barrier, but it is placed in close proximity to the myocardial tissue. Safety testing. So the average resistance of the human body can be 1 to 2 kiloohms. There is no physiological difference between let go currents at commercial frequencies of 50 to 60 hertz. So it's a fairly flat response across this range here, but the body does respond to that quite significantly. And as the current frequency increases, the body becomes less stimulated. All of the parts of the body, the cardiac functions, the nervous system, the muscular systems, are all sensitive to these physiological effects at 50 and 60 hertz. And then as frequency goes up into the higher ranges, such as those used in electrosurgery, the body doesn't become stimulated by the electrocution. So electrical safety testing in healthcare organisations is an important practice. It should be guaranteeing that everyone within that facility is safe. That's clinicians, visitors, and any vulnerable patients. The primary safety purpose is just to prevent any patient, operator, visitor being exposed to currents that are not part of the operational device. So anything outside of the operational device, which we talk about as leakage currents, so those are non-functional currents, are what we're trying to avoid and what we're trying to limit exposing any individual to. And there are several specified safety barriers within the circuitry of equipment which guarantees that these leakage currents are not going to be a hazard to the user and the patient. When we talk about electrical safety in NFPA 99, we're just ensuring that it continues to be performing safely during its medical device life cycle. One of the main ways of doing that is for a grounded or earth connection, and this applies to class 1 equipment only. It relies on a protective earth, and that provides a low resistance earth path for all leakage currents to flow to the ground if a patient or user was to come into contact with any exposed conductive parts. Any large fault currents are going to flow down that very low resistance path rather than for a patient or user. In addition to that, you have got RCDs, current breakers, which will interrupt any voltage supply if hazardous leakage is detected on that ground path. So it's got two methods of protecting the patient. One is by removing that current away from the individual, but also by tripping any currents, by tripping the current breakers, RCDs, etc. There's insulation. This is another method of protecting users and patients. Basic is providing just sufficient dielectric strength. So we'll see this on class 1 devices. Supplementary, now this will sometimes be referred to as class 2. It uses supplementary protection and is provided by a double layer of insulation. So there's no earth connection required. You've already got that safety barrier by introducing an additional safety barrier. And then we've also at the bottom here, we've got electrical safety testing, which ensures that all these parameters are still performing correctly. Do we have a breakdown in insulation? Are the ground connections still safe to use? Have there been any breakdown in the connections? So we're just ensuring with electrical safety that all these things are still performing as they should be. The objective is to test for breakdown. It gives protection against both the macro shock and micro shock factors. Legal liabilities, you're protecting patients, staff and visitors at all times. And electrical safety is done at various stages in the product's life cycle. There's acceptance. So most medical electrical equipment is designed and developed against the 60601 standard for the strict rules of the design of medical devices. We know that the primary safety process is just to prevent any patient or operator from being exposed to those currents. So an acceptance test is just to ensure that it's as it was when it left the facility. PPMs and post-repair, safety tests, regular maintenance carried out by biomeds, the end users in healthcare, help to detect any potential defects. Should also be mentioned that there is potential risk in some cases from fraudulent devices, not so much in the modern world, but there are cases where fraudulent devices and parts slip through the net, and if this occurs, then electrical safety checks, visual checks, performance testing with performance analyzers will likely detect any problems. Protective ground, this provides current path in case of leakage and fault currents. There are several types of class 1 medical electrical equipment that have exposed conductive connectors. Patient beds are a good example. So we need to ensure that the current path is there available if there's fault currents on those exposed connections. It proves protective integrity from touchable conductive parts of the medical electrical equipment to ground. And routine testing of earth bonding is just to ensure adequate connection between these conductors and the mains plug. So we've got good grounding between the protective earth and any exposed connections. Now, over time, what can happen is connections or bonds within the unit, they can fail due to increase in high workload, high stress medical environments, and these poor contacts and any film resistance that builds up between those contacts can be imperceptible to a visual check. So we need to double check that these ground bond values are still within the specified limit. Fault current, so we want to also ensure that the values are within in the correct. What are we measuring? We're using an ohmmeter to measure resistance between exposed conductors and protective earth. The lower the values, the better, but limits will be stated in the specific standard. Measuring currents are not always mentioned. So in the NFPA 99, the values, the current values are not necessarily mentioned. They just give you examples how you can measure the resistance between these 2 points. But the majority of users will be utilizing an electrical safety analyzer, which will have a method that's approved by that standard. So I've just got some questions. Typically I answer questions at the end, but someone's asked about, while we're on this subject, what's the difference between earth and ground? Terminology primarily. What you'll find in the US, ground is used more commonly, whereas in the UK and other parts of the world, earth is used. So effectively, there's different terminologies that are used between different places, and it's all really to do with language. But there are nuances even there. But the primary difference, I would say, American English, you're going to be primarily using ground bond, and British English, it tends to be ground bonding, earth bonding, sorry. So leakage current that is non-functional. ANSI/AMI ES 60601/1/2016, derived from the international standard IEC. So in the US, ANSI/AMI is used for electrical safety testing at the medical device manufacturer level. This is not at the service level, the BMET level. This is a different standard entirely, but it's all derived from IEC 60601. So it's unavoidable. It's a result of stray capacitive and resistive dielectrics. Current at commercial frequencies flows from live to earth or hot to ground. Again, that's terminology. I said live to earth, but hot to ground is what's used within the United States. So all mains powered equipment is powered to ensure, when mains powered equipment, it's designed to ensure safe levels of leakage current are retrieved. Any powered device, you cannot eliminate leakage completely. What you're doing is trying to limit within a safe limit. During development, high levels of isolation from electrical potentials to accessible conductive parts are required. So earth and enclosure type leakage currents have limits that are reflected from the first side with macro shock. Medical electrical equipment is designed to have even higher degrees of isolation, and this is mainly due to the introduction of patient connections, applied parts, and the risks of microshock. So class 1 ground leakage travels down the earth path to ground within a medical device in a standard TN system. Current in the live wire carries both the functional current and the leakage current, whereas the neutral wire only contains the functional current. And there is a method within a different standard, which is 62353, whereby the leakage current is actually measured by looking at the imbalance between these two connectors. But the preferred method is to measure it directly. So we've got the live carrying the functional and leakage current. The leakage current is lost through capacitance within the medical device. It travels to the enclosure and down the protective earth path or the enclosure, and we can measure that using a safety analyzer. Now, the earth connection is also there to keep the user or patient safe in the event of whereby you've got very high levels of current flow from the circuit. So the NFPA 99 does specify the configuration of the mains for electrical safety tests. So we need to be on a tera-neutral system. This is where neutral is at the same potential as ground. It's 120 volt live. Leakage current is typically measured from a high potential to ground, and this is to ensure that the highest possible leakage is measured. On the highest potential, it says 230 here, but obviously with 120, it should be 120 to earth or 120 to ground with the highest potential possible. Now, on an IT system, the highest potential from phase to earth is not achieved. So leakage currents are limited to the isolation levels of the supply. And no valid leakage limits or measurements can be taken because the safety analyzer is unable to produce an internal ground at half that line voltage. which is actually what's stated in NFPA 99 in one section, where it's an adapter can be used to temporarily produce an internal ground. You'll see that in section 10. So that eliminates this issue with the IT system. If you can get an adapter which will produce an internal ground, then you can perform electrical safety tests through that. Now, if you are on one of these systems, a Rigel safety analyzer will alert you of that. It has a IT system detection and notification, which is quite a useful feature as it lets you know if the system you're testing on is correct. Secondary ground path. This is a common problem, but often goes unnoticed. It occurs when medical equipment is connected to other equipment, such as data lines, monitors, endoscopy, or even water. Now, the image on the right represents an example of a secondary ground connection, and this is via a data cable to the PC. Most of the current is taking the path of the least resistance. This is grounded as well, so you're likely to get a value that's below 1 ohm. And the safety analyzer is measuring a much lower value because the resistance is higher. There's a body model within all safety analyzers, typically 1 kilo ohm. So the electrical current is going to take the path of much lower resistance. And again, if we talk about the 1 kilo ohm body and a value of 1 ohm or less, then if we look at the example in this image, comparing to the 1 k ohm resistance of the body model, the secondary earth ground is, okay, we've given it an arbitrary value of 1 ohm in this instance. Values are much less than can be expected via an alternative earth path. And that means you're going to get errors of 1,000 times or more. It's a significant jump. Again, though, these types of issues are detected automatically by our safety analyzers, and they do have a warning if a secondary ground path is detected. So all tests are for electrical medical equipment that can be divided into 2 categories. We've got class 1, which is earthed, and class 2, which is double insulated, which we spoke about in the first couple of slides. The symbol on the left is for class 1, and the one on the right is class 2. These are typically found on the rear of the instrument, close to the power supply. Sometimes class 1 will be symbolized with an equipotential symbol, which is just like this, but with an upside down triangle at the bottom. If you're unsure of what class the device is, then you'll need to contact the manufacturer or look at the service manual, but typically this will be highlighted. So what standard are you using first when you're testing a medical device? Well, to this webinar today, we're talking about NFPA 99, but in some cases you might be using a type test standard like IEC 60601, or an alternative recurrent testing standard to NFPA 99 like 62353. What else is included? A visual test that highlights most of the issues you're going to get with a medical device. So that's housing defects, cabling, does it have the correct fuse rating, just looking at the device as a whole. Is the instrument class 1 or class 2? What connections does it have? Does it have any exposed metal work? Are there applied parts? In some cases, you need to understand what the classifications are. In NFPA 99, we don't need to know that. Applied parts are all classified as the same type of applied part. So when you're performing a test, those electrical patient connections can be grouped together. This is something which compares the different standards and codes. So standard is a document which contains technical definitions. It has guidance for manufacturers, for procedures. It's not necessarily mandatory, it has mandatory requirements, but compliance to that can be voluntary. A code such as NFPA 99 is a document that's been enacted into by regional or national authorities, and they have jurisdiction to state that an engineer or a biomed contractor, they're legally obliged to comply to these tests and these codes. Adhering to standards is best practice. It's good for being integral to good quality management systems. But NFPA 99 is something that's adopted in the USA to North America and is required by law. And the tests from all the other standards, they're based on IEC 60601. So you'll see here NFPA 99 uses this standard to derive its testing from. What it effectively doing is simplifying those tests to make it easier for the end user. This is for medical device manufacturers where they might be doing more stringent testing. NFPA 99 has been simplified to make things a little bit easier for the end user, because quite frankly, we haven't really got time to be performing the level of testing that comes from IEC 60601. So NFPA 99. Firstly, I'll talk a little bit about the categories, and it does apply to electrical safety. There are 4 levels of system categories that need to be considered, and each category is based on the risk to the patients and caregivers in a facility, in any healthcare facility. Now, it's ultimately up to the facility to decide which categories the equipment falls under, and this is done via risk assessment, but the categories are typically classified that way. So we've got, in the first slide, we've got category 1. This is equipment failure for any duration is likely to cause serious injury or death, e.g. operating rooms. And then we've got the category 2, which is equipment failure is likely to cause minor injury. Category 3, equipment failure is unlikely to significantly affect patient care. An example of that is a dental room. And these are given within the NFPA 99 code. Now, it's important to note that the examples below may vary depending on the actual impact and the risk that's present. As a result of this, all areas must have a risk assessment for any categorization, and they do have an impact on electrical safety testing. For example, there's some electrical safety tests that are omitted for category 3 and 4 areas. I can't remember exactly what they are off the top of my head, but we'll talk about that shortly in the next few slides. There are some tests which don't need to be performed in these 2 categories. Now, if you do perform them, I mean, there's no harm in that. And that's ultimately up to the organization. So visual inspection, this is aligned with ANSI AMI ES 60601. We know that the performance criteria of the healthcare environment in its entirety, and not only the performance and safety of the equipment itself. So that's one thing that NFPA 99 differs from. It's talking about the healthcare environment as a whole, not just related to the medical appliances. And a good example of that is ground and strain relief test on receptacles. They're not medical devices, but it's something that NFPA 99 states. So we have to look at that as part of the procedure. We're mainly going to be looking at electrical safety tests. So this webinar is going to focus primarily on that equipment. It's just important to know that it does refer to the facility as a whole. Each manufacturer will produce recommendations for the intervals of preventative maintenance procedures for the equipment and recommend intervals for testing. In some of the previous revisions of NFPA 99 that I've looked at, there have been statements of 6 months in critical areas and at least every 12 months for general areas. Now, I've noticed in the latest revisions that these statements are starting to be phased out, but the risk there is still present. So they're still good guidelines to follow, even though they have been phased out of the standard. The regular testing just ensures that the medical device is free from any hazards. So visual inspections of the equipment help to identify any hazardous appliances in the healthcare facility fairly quickly, and they form a critical part of general safety inspections during the functional life of the medical equipment. Around 70% of all faults are detected during this visual inspection. And now it's not just BMeds, it's not just the biomeds, the engineers within the hospital. All staff should be expected to be observant of the condition of the equipment that they use, and if faults appear, then that should prompt them to send it to the biomed department for repair and removal of the appliance from service. Now in NFPA 99, there's no formal or documented visual inspections that are required by the individual. But that being said, a checklist wouldn't hurt. It'd be handy to have one within the workshop. Within some of our electrical safety analyzers, we do have a visual test check at the beginning of the test sequence. I'll quite often add that in as part of a test sequence, just as a reminder before an electrical safety test that all the visual checks have been made. So what does a typical inspection include? Well, we're looking at the case or chassis, looking for any damage or cracks. We're looking at frayed wires. We're looking at damaged plugs. They're all effectively just common sense faults that, as experienced biomeds, you'll know what to look out for straight away. One thing to not forget about is that non-patient care related electrical equipment. This must also be inspected by staff or other personnel now. And it's not, so this is not just equipment that's owned by the facility, but also any patient-owned appliances which may be used in that patient area and may come into contact with the patient. So it's not just medical devices, it's also anything that's non-patient care that's brought in, and that is specified in the NFPA 99 code. So we know that Class 1 equipment is a ground conductor, so leakage current on the chassis or enclosure can flow to ground to prevent harm to anyone. Grounding is a proven safety measure for preventing electrical shock. Measuring and checking that resistance between the appliance and ground ensures that the safety measures continue to work throughout the device's lifespan or life cycle. There are a few diagrams for the resistance meter in NFPA 99. This example below uses the 2Y method. It's simple, but it's effective. Now, majority of users are going to be using some type of electrical safety analyzer, which will have a resistance meter automatically built in. The measured values do vary from standard to standard or code to code, but in NFPA 99, 500 milliohms is the threshold for failure. Any value measured below this is a pass. Think of it like this: if the human body's resistance is 1 to 2 kiloohms, or the lowest value 1 kiloohms, even at the maximum allowable value of 500 milliohms, that's still 2,000 times less than the leakage current that would flow through the human body without that ground bond. Even at the maximum 500 milliohms, you're still going to have 200 times less leakage current flowing through the body than it would through that ground bond. And that's why we're measuring that value. So leakage measurements can be broken down into ground leakage, touch leakage, and patient lead leakage. No body model is mentioned in NFPA 99. However, the frequency response characteristics must match the body model found in AMI ANSI ES, that should be 60601. So to measure those currents, you just need a meter that has frequency characteristics that match this body model on the right. Without putting myself out of a job, you could, of course, make this up in your own workshop with a voltmeter and some basic components and resistors, capacitors. You would also need to simulate the fault conditions such as open ground, which is found in NFPA 99. That's one of the reasons why workshops do use dedicated safety analyzers and just ensures that you're getting the right measurements. So ground leakage tests are not going to be performed as often as your other leakage tests. They're only specified for fixed equipment in category 1 and 2 spaces before you install the equipment. So you're only carrying it out on these specific fixed equipment devices, and you're only doing it before it's installed. So it's not as often you'll be performing these tests. And this is just to ensure that all leakage current flows to from the measurement circuit to the measurement circuit of the safety analyzer, and this test is done before those grounds are then connected. So the leakage current is measured from the ground conductor of the power supply to the ground of the fixed appliance, and the current limit for this test is 10 milliamps, and the power is switched in both the on and off positions. So you're carrying out 2 tests. Touch current tests simulate a human body contacting different parts of the equipment. That's any equipment that will flow from an individual, from the equipment and chassis, or any type of accessible part not intended for patient treatment, no patient leakages or patient applied parts. This is during normal operation. It applies to all portable medical electrical equipment, and unlike IEC 60601, there are no fault conditions introduced, except that ground is open. The ground is open, but there's only one fault condition that's introduced. Touch current tests, they simulate a human body coming into contact with different parts of equipment. The measured leakage current values are compared with acceptable limits. 2 measurements again are taken, both in the on and off positions. Only one measurement is taken if a switch is not supplied. Obviously, you're just going to be carrying out one, but if it does have a switch, then you use the on and off. If the appliance is permanently fixed to ground, touch leakage is just performed in situation without ground open. So you're just putting the probe onto the medical device that's fixed to measure the leakage that way. And this has a limit of 500 micrograms. There is a table at the end which does highlight that. So the current must be measured using the power supply directly from a standard grounded system. This gives that highest possible leakage outcome, which we were talking about earlier. But we do have that detection system if you are not on that non-standard system. You can obviously use that adapter again to temporarily ground one side of the isolated power supply, but it must be performed with obviously a suitable adapter, which is plugged into an outlet on that system. That, for obvious reasons, that adapter also must be removed from the measurement once it's completed. So you're only using that adapter for testing purposes. It's obviously a hazard and needs to be carried out by someone that knows what they're doing. But it's a good suggestion in NFPA 99 for those isolated systems that we quite often come across in healthcare facilities. There's also a statement in NFPA 99 on touch leakages when one power cord supplies the power to multiple devices, which is an interesting statement because compared to other standards I've looked at, it avoids confusion when testing things like stack systems, because that often causes a little bit of issue when you've got multiple devices, but also devices that are stacked and considered one system. It does cause a little bit of confusion. And here in NFPA 99, it kind of avoids that confusion. It states that if a fault were to occur within the ground connection of the power cord, then the sum of the currents from each individual device would flow to Earth via any human contact with a chassis. So the touch current is measured as a whole. And that group together limit is 500 microamps as normal. There are some suggested methods of lowering the sum leakage if you're getting higher values, and that's just done by separating the device grouping and testing them individually. But it's only required if the values exceed that 500 microamps when one power cord. So you're only doing that as an investigative method. Similar to how you would do it with applied parts. If you've got if you're testing applied parts and the sum of the leakage is higher than the test limit, then you're just going to break it down into individual applied parts. You're going to do the same thing here. You'll break down each medical device to see where that fault is coming from. Now, what I sometimes get asked over in the US for touch leakage is, well, where there's no exposed conductive surface, how am I going to am I going to test touch current if there's no exposed conductive point? Well, in previous revisions of NFPA 99, now this has disappeared, but it's still mentioned in IEC 60601, you can simulate an exposed conductive point by placing a 10 by 20 centimeter metal foil in contact with that exposed surface. And then that part is then considered the exposed metal surface of the appliance, and then all appropriate tests can be performed using that foil. So that then becomes your exposed conductive surface. That's one way of doing it. Or some people would, if there's a protective paint, they'll scratch off that paintwork and try and get a connection that way. But this is one way of performing that test just without causing any damage to the equipment. Patient lead leakage current tests. Patient lead is any lead that has direct conductive contact with the patient and is referred to as an applied part. And that comes from ANSI or IEC 60601. Now, this does include non-invasive and invasive connections such as ECGs and pacemakers. Consequently, non-isolated electrical patient connections have lower leakage limits of 100 microamps, and that's to reflect the associated hazards. In earlier revisions of NFPA 99, it did state that each individual applied part to ground must be measured. However, in the last two editions, including 2021, patient leads are grouped together and measured as a whole. These are always shorted together and just measured as total leakage, the sum of total leakage. Testing should be carried out using this circuit on the right with the device powered on. The leakage current limits are 100 microamps for the ground wire closed and 500 microamps for the ground wire open. As in this example, we've got the ground open, but the fault conditions will be introduced by the safety analyzer. And just for clarity on the tests, these are the limits and the single fault conditions for each test. They're in the code clearly, but might be useful to you to have. I'm happy to print a copy out and maybe even stick it on your wall, but it's always handy to have that for reference. I can make these slides available at the end if you'd like to have a copy of the presentation. Just for a quick point of reference. So best practices, it's the facility's responsibility to identify which patient care related electrical equipment requires regular checks. Each device must be tested in accordance with NFPA 99. It's done at acceptance and during any maintenance carried out on the equipment that may affect the electrical equipment. I mean, best practice really is every time you open up a unit and make any changes, any amends, you carry out an electrical safety test. There are also recommendations on the minimum periods for safety checks whilst at service, and this is at least every 12 months. But the responsibility of the duration of retention of test records falls on the healthcare facilities records policy. So with alternative equipment maintenance procedures, this can vary widely once you've got evidence on the safety and reliability of the devices that are in your workshop. So it's only up to the healthcare facility to decide this. You must ensure you appreciate these two factors here. Again, we've got the option on the safe tests and the Rigel 288 where those issues, if they do come up, if you're on an isolated system or if there is a secondary ground, then the safe test is going to highlight that, as is the 288. So our products will have that feature. Best practice for records. It does state in NFPA 99 the minimal standard of documentation required for routine checks of the equipment. So these are the three things that must be notified. So each record must define what was tested, the test date, and whether it passed or failed. So these are the minimum requirements. Test protocols may have the electrical safety measurements. I mean, it will help if you ever have any legal issues or any problems with a medical device. If you've got recorded values, then it does help in some ways. But NFPA 99 only specifies these three things: the device that was tested, so the unique identification code, the date that it was tested, and whether it passed or failed. It's quite simple. At the very minimum, these are the requirements. Test protocols should be developed to ensure consistency for each electrical safety check and record. The aim of electrical safety in NFPA 99, and that in all electrical safety standards, is just to limit the leakage currents that can cause any injury to a patient or user. So it's always best practice just to test where a risk to electrocution may occur regardless of what the minimum requirements of the standard or code are. It's always worth looking at even what the manufacturer recommends and sees, and look at what they've stated in their own service manual, and always looking at that for their guidance. And as it states here at the bottom, service manuals may specify additional checks, but the NFPA 99 code is law and must be followed first and foremost regarding electrical safety. The NFPA 99 handbook stipulates about the use of these. An analyzer must simply produce the results you require accurately and repeatably. So how do you pick an electrical safety analyzer? Does it produce the results you require? The measuring device frequency response characteristics closely match the body model in ANSI-AMI. Does it have traceability of measurement results? Are the results you're getting from your device accurate? Because you need to follow that back via a traceability period through calibration to ensure that the results that you're getting accurately are traceable as well. Ultimately, it's all to do with, if you buy a safety analyzer from any manufacturer, they're going to have all of these factors. So it's all about test convenience. Do you like the user interface? Do you like the test duration? Do you like time efficiency? So it's ultimately up to the end user which safety analyzer they use. If it's from a reputable company, then at the end of the day, it's up to user preference.
So now I'm just going to go into a demo of the SafeTest 99, and this is our manual electrical safety analyzer with applied patient lead connections. So I've just run through that demonstration, and it follows all the NFPA 99 tests we've just gone through in the presentation.
Okay, that's good. And one of the most important parts about an electrical safety test is the initial visual inspection. So we're looking at a couple of things. Does the device have any cracks? Is it damaged? Is it in general good condition? So it's all common sense things to look out for. We also look at the cords to see if there's any frayed wires, if the plug's damaged, does it have the correct amperage rating. And we can also test the stress relief, because that's part of the NFPA 99 schedule. You need to look at the stress relief of the cord. Does it still have good integrity once it's been put under that strain? So one way to do that is just during the ground continuity test, which is the first test when performing electrical safety. So I've got my medical device here. Make sure you can see that all okay. Looks good. I did disconnect the alligator clip because this device doesn't have a point where I can connect the alligator clip, so I'm just using the 4mm probe. So I'm going to zero that out again. So I connect the probe between the black 4mm socket on the SafeTest 99 to the ground receptacle on the device under test. Still close to zero. I think we're okay, but I'm just going to zero it out anyway. Now I can test ground bond. So my device under test plug goes into the receptacle of the SafeTest 99, and then I plug the 4mm probe into a point where I'm going to get a good connection. So, well, that fits in there quite nicely. There's a good connection, so I don't even need to hold that on there. It's in there quite snugly. And then I'm looking at the result here, 0.07. So I'm going to pull up some of the slides from our NFPA 99 presentation. So you'll see on screen ground bond tests. As long as the threshold is below 0.5 ohms, then we can prove that it's a pass. Now I can check the lead for stress relief just by moving it around a bit to see if it's still within those limits. So I'm creating some stress on the leads, and it's still looking pretty good. So that's a good IEC lead there. We're not getting any issues. So okay, we're happy with that. Ground continuity test has passed. We can now move on to the next test. So if I scroll down through the presentation, with first we've got leakage current tests. That's ground leakage, touch leakage, and patient leakage. Ground leakage is for fixed equipment in category 1 and 2 spaces only. So this isn't fixed equipment, it's a portable device. So we don't need to perform that test. Very rarely can be performing a ground leakage test. So we move straight on to touch current tests, and this simulates a human body contacting different parts of the equipment. So on the safety analyzer, hit the home button, and then we select F2, and that comes up with a list of the different leakage tests that the Safe Test 99 performs. Touch current is F2, select that, it's simulated by this touch symbol. And we see from the slide that it says ground switch is open, so we hit this button here. We can see that the relay switch is opened, and then we perform 2 measurements, power switching in both the on and off positions, and to activate the device we hit the green button, and that's now performing a touch leakage measurement. And it should be in both the on and off positions. This power switched in the on and off, so I'll switch this device on. And I take 2 different values once the device is powered up. Okay, slight increase in the leakage values there, but still below the limit of 500 microamps. So I'm happy with that. And then we can move on to the next test, which is the lead leakage current tests. So I've got my ECG connections here. I've already got some snap adapters in the box, so I can connect each of those. It doesn't really matter the configuration of where these go, because we're just performing electrical safety. There's no ECG simulation. So I select that, and then I disconnect my probe from the analyzer. Hit the red button, that stops the test. I can now take the probe from the rear of the analyzer, that's no longer needed. And then I connect the ECG box to the 4mm socket where the probe just was. Patient leakage is simulated here, so that's F3. And if I now scroll down to the next slide, we've got lead leakage current tests. So that's for all leads that are in direct conductive contact with the patient and is referred to as an applied part. So we've got 2 different leakage current limits here. 100 microamps for ground wire closed and 500 microamps for ground wire open. So again, hit the green button. Device switched on. And we've got ground wire open from the previous test already. So ground wire open, we've got a limit of 500 microamps. And then ground wire closed. So we've got 100 microamp limit there, well within the limits of NFPA 99. Medical devices are typically developed to have very high levels of isolation, particularly for the ECG connections, so you're unlikely to see high levels of leakage. But you've got a significant limit for NFPA 99, so you're unlikely to see high measurements unless you've got a fault within the device.
And so now I'm going to run through the Rigel 2.8 electrical safety analyzer. This is our automated comprehensive electrical safety analyzer. And there's also a demo there with the new and latest application for downloading test reports to your phone. So we connect up the device in the same way that we do with the SafeTest 99. It's the same connection, so firstly we need to zero out those leads that we've got connected to the rear of the 2.8 safety analyzer, and then we can connect that to the rear of the analyzer. While that's zeroing out, I'll just connect up these patient lead connections to the ECG snap adapters, and then after this I'll plug in the earthbound lead to the rear of the analyzer, much like we did with the SafeTest 99. Now this is a fully automated safety analyzer, so it can be done using through the menu settings, select auto mode, and keying in asset information. It's fully automated, so we run the test sequence based on the NFPA 99 guidance for this type of device. As you can see, there's 10 applied part adapters, so just select automatic mode, plug in the device on the test, key in an arbitrary number for asset details, check that we've got the correct standard for a class 1 device. See, applied parts are done. Literally it's running through this test fully automated. There's not much we have to do except just follow the prompts as the test runs. So you can see this is a lot easier than performing a test with a manual electrical safety analyzer. But it's all up, at the end of the day, it's up to user preference. What works for the end user best. Some people prefer to carry out manual tests with the function keys on the front. But for others, it's all about recording results and running through a fully automated procedure where those results can be saved and uploaded to your asset management system or stored within any of the systems. So next test, chassis leakage. And again, I've seen on screen here the touch current tests. It's identical to the test we performed with the SafeTest 99, except this is fully automated. So telling us to switch the device on and off throughout the test. And there we go, we can hit save, F4. That will save the results. Now I can show you how to do the downloading of those results to the app. So this is on iOS, we do have an Android app as well. We open up the app first on our phones. This has already been paired to my phone, so I don't need to repair it. It will show up on the screen. If you do need advice on how to pair it, just let me know. You just select Apple devices for this particular app, and then once the tester is connected, the Bluetooth device should show up within the menu settings there. So it's connected. We wait till the 2.8 says send and connected. Now all of our test results are sent to the application. I'll select the last one at the bottom. This is the latest PDF, the test result we've just performed, and there we go, the results are all there compiled into a test report PDF, and you can send that out to via email, share it as you would any other PDF. So you might be asking what the other safety analyzers in our portfolio do. The first one, SafeTest 99, has 10 applied parts. It's a device that we use for testing any type of medical device within a facility that has patient leads. The second device is a fully comprehensive device. It tests all standards, up to 10 patient leads. They can be isolated, does insulation tests. So again, that is our flagship device. It does test every single parameter that's required. But in some cases, the facility that's being worked in doesn't need such a comprehensive device. So what's the difference between those two devices and the other three that we have in our portfolio? So the first one you see on the left there is the 62353 Plus. That is much like the 288. As you can see, the form factor is the same, but the difference is it only has 2 patient leads. It comes with 2 cables as opposed to applied part box. Doesn't have Bluetooth, but you can transfer data in the same way that you do with the 288. It's just via a USB connection, and it only tests to local standards like NFPA 99, but it also does IEC 62353. So it's not going to be able to perform any tests, or at least not all of the tests, to IEC 60601. So that's a slightly cheaper device than the 288, but it comes in at a better price factor, but it doesn't have as many functions as the 288. And then if we move across, there's the SafeTest 50. So that is much like the SafeTest 99, performs very similar tests to the NFPA 99 code, but it doesn't have the patient lead connector box. So this is ideal for facilities like care homes that are just testing things like beds, things that don't have any applied parts. So it's effectively your SafeTest 99 without any patient leads. And as we move across to the final one, the SafeTest 60, this is a device that tests insulation. So it's much like the SafeTest 50 to its left. The primary difference being that it's able to do insulation tests, which is sometimes a requirement for manufacturers or people that are carrying out alternative tests to what's recommended in the local codes and standards. So that really gives you a quick overview of some of the other testers we have within our portfolio and what those differences are. I'd like to thank you all for taking the time out to view our webinar today. I hope it was useful. If you have any other questions or you need any one-on-one demonstrations, any further queries on the application, then please feel free to either reach out to us directly or just raise a support ticket on our website, and we'll be able to help you out as best we can. Again, thank you to TechNation for allowing us to host this webinar today. They've been a real help to us in getting this webinar set up, and I hope to see everyone on the next webinar. Thank you.
Great. Thank you, Lewis, for your time and for a great informative presentation. If you have any questions for Lewis, please email him directly at lewisl@rigelmedical.com. I'd like to encourage everyone to visit today's sponsor to learn more about the services they provide for our industry. So please visit rigelmedical.com. As promised, the answer to today's trivia question is Michigan, closely followed by Washington. So congratulations to our winner, Martin O'Brien in Wisconsin. Enjoy your AirPods. Just a quick reminder, you can obtain your CE certificate by completing the post-webinar survey. The survey will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit from the ACI, and you'll be able to download your certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. If you've missed any of our past webinars, please visit webinarwednesday.live to view our whole webinar archive. We'll be back next week with another webinar and another 10th anniversary prize. So visit webinarwednesday.live for more details and complimentary registration. Thank you once again for your time today, and I hope you enjoy the rest of your day.